Hi everyone. Today we are going to discuss about the EFI hop type CPU. So this EFI hop type CPU mainly contains two information, which is the size of the memory space and the size of the IO space. Usually we have this EFI generic header, right? So which mainly used to contain the length and the type. Okay, and then we have these two uint8 attributes, and then we have the reserved bits for the future usage. Okay. So now the size of the memory space identify the maximum physical memory addressability of the processor, right? So assume there are two processor A and a processor B. Assume both are 64-bit capable, right? So even though both the CPUs are 64-bit capable, the processor cannot handle the entire 64-bit address range. A processor A can able to handle 512 GB, or maybe a processor B can able to handle suppose a memory address of 4 TB, right? So this change is mainly a silicon requirements. They used to do some power management stuffs, right? So to save the power, ultimately they used to reduce some physical addressable lanes and other usages as well. Okay, so now with this information, right? So what is the purpose of building this hub, right? So based on the PA specification, so what does it says? The CPU hub producer by the processor executable content in the hop producer phase. Meaning, so as you know, the hops is used to be produced in the PI phase. So which means the CFI CPU hop type is going to be builded during the PI phase. Okay, and it describes the processor information, right? So the processor information which mainly deals with the memory. Okay, so which is this address and the IO capabilities. Okay, and this hop mainly consumed by the GCD. Okay, so what is this GCD, right? It's a global coherence domain, right? So which is used to manage the memory and the IO resources for each processor. Okay, so as I just took the example of processor A and the processor B, right? So to know or to let the GCD know that this processor is capable of handling this is the memory range. So using this hop, we are going to let GCD know, which is Global Coherency Domain Services. Okay, so now in our emulator package, so where exactly we are building, what is the maximum size for this memory space we are giving, and then what is the size for this IO space we are giving, we can check. Okay, so let's search this. Okay, so here we have this, right? So ultimately, let's see where exactly it is getting created, right? So we have this API called a build CPU hub, right? So it used to take these two arguments, right? So one is the memory space and the IO space, and which ultimately is going to create the hub, right, of a type, a hub type CPU, and the size of this hub, and then it used to assign these two input arguments, which is this one. Okay, and then we have the result fields as well, right? So we are going to zero mem this. So which means the caller will call this API build CPU hub. So if you look at the instances, there are many instances, right? So ARM is going to use this addressable bits, and then the IO they used to get it from the PCD, right? So now for now, let's stick to our emulator package. Okay, so now in this emulator package, so we can see uh, build CPU hub with 57 bits of addressing. Okay, so now let's see what is this bit 57, right? I'll open the calculator. So one left shift by bits 57, right? And which is this one. And now I will go to this base.h, and then I will search for this number, right? So which is 128 petabyte. Okay, and the other way of checking is here we have this bit 57, right? So here we are passing this memory space as a 57, right? So which is nothing but a bit 57. So this bit 57 is nothing but this two followed by zeros, which is ultimately 128 petabyte. So which means this emulator package is capable of seeing a memory range or capable of handling a memory range till this 128 petabyte. Okay, and then we have the IO space, which is bit 16. And if you go to our bit 16, here we have, right? And this bit 16 is nothing but 64 KB. So which means this emulator package is having 128 petabyte of memory space, and then it is going to have 16 KB of the IO space. Okay. So now where exactly this hub is going to be consumed, right? So just we saw from the PS specification, right? So this is mainly used by our GCD, right? So now let's go back to our gcd.c file. Okay. And now here, let's search for um, um, hub underscore type underscore CPU. Okay. So now this is where we are getting that hub, right? So in the part one of the hub sessions, we saw how to get the hub, right? So here we are using the hub with the help of this type. Okay, and once we get that hop, so we used to print we used to get the memory space and the IO space. Okay, so what exactly we are doing with by getting this memory space? So ultimately you can see it is used to specify the end address of the processor which it is capable of handling the memory. Okay, same applies for the IO space as well. Okay, so now let's try to print, right? So what is this memory size of the memory space and the IO space it used to come, right? So here we are building this 57 and 16, right? So the same information should be reflected here. Debug underscore info, and then here let's try to print. I will use the decimal percentage D. And then I will do the CPU dead loop. So let's halt it here on the IO space, IO space. So now let's build it. Okay, EDK setup, and then we'll do build. We'll wait for the moment. Okay, so build is completed. So let's try to run it. So we'll go to build i32 vs 2019 i32, and then we have this WinHost. And if I run this, whatever the debug print which we have added, it did not came. This message is coming from the PI. And now let's go ahead and look at this GCD, right? So this GCD is part of this PI main, sorry, Dixie main.inf. And now let's go to our emulator package.dsc, and then let's search our Dixie main, right? So let's see whether we have our debug library or not. So here we have our debug library, and then we have the serial library, and still it's not the debug print is not coming out of this Dixie main. It's because probably for the Dixie, it used to be dependent on some protocols to initialize the serial memory, and maybe that protocol may not be exist. So let's see. Yeah, here. So there is a constructor called emu constructor lib, and this emu constructor lib is ultimately is going to assign this global variable, which is emu thunk, right? So from this emu thunk, they used to do the serial write. Okay, and now so since it's a Dixie one, so since it's a Dixie driver, and so still we are in a core module, right? And that's the reason this constructor did not get called, which ultimately we did not get any print out of this GCD. Okay, so now how can we confirm what is the value of this and this, right? So let's open the Visual Studio now. So this is ultimately a source level debugging on the emulator package. Okay, so I will open continue without code. So now we will open the Visual Studio Code. We'll drag down this. Okay, and now we have this WinHost here. And now we will click on this start. Okay, so now we got the error. So first let's close this. Now let's do the start. Now we can see it is executed, right? So now we will do Control C. And now what we will do, right? So we have this C file, right, where we have added this. So let's open this and we will drag to this in the VS Code. And now let's search for this CPU dead loop, right? And now right exactly here, I'm going to add the breakpoint. So breakpoint, insert breakpoint. Now I will start this. So now our breakpoint will hit here. Okay. So now start. Okay. So now we can see it came here and it is hit at this breakpoint. Okay. So now you can see the CPU info hub and currently it is not initialized. So that's the reason it is unable to read the memory. Okay. So now let's do step over. And now the current instruction pointer is pointing to this, so which means the CPU hub is updated. And here we can see the size of the memory space is 39x. So that 39x is nothing but a 57, right? So let's see 39x. Okay, so which is nothing but a 57, which is 128 petabyte. And then we have this IO space, which is 10. So which is ultimately a decimal 16, right? So which means whatever the hub which we have built in the PI, so that same data we can get it from here. Okay, and now we have built it, right? So now, so where what is the other places where this CPU hub type is being used, right? So now ultimately we need to create some page tables, right? So during the page table creation also this hub being used. Okay, so let's see. Now it should be outside of the MOTM. So virtual memory, this is OVMF. Okay, so now in the OVMF package, okay, so what we are doing, so we will get this hub and based on that memory space, right? So which is a physical addressable bit which the processor is capable, right? So that we are going to assign it to this physical addressable bit, and based on that we are going to create the page table for it in the OVMF package. Okay, on the real silicon, so let's see, right? So we have this virtual memory, and this is being used by our UFI payload. And then we have our Dixie IPL, which is mainly used in our client processors, right? So now first we will check this hub. So if this hub is if the hub is available, so then we will read that processor capability from the hub. Okay. So if the hub is not available, then we will read it from the CPU ID. So this CPU ID will give us what is the physical addressable bit that processor is capable of seeing. Okay, and if the CPU ID is not supported, then it fall back to this bit 36 based on the Intel SDM. I think it's based on the SDM. Okay. Okay. Yeah. That's it for today. Thank you.